meantime, we're going to crash on dealing with two-dimensional data and categorical data. Last time we introduced some visualizations, some obvious visualizations for categorical data when there are two and possibly more variates. I want to continue in that fashion today. And as you see, I've sort of subtitled this one, Visual Reasoning. I want to think about actually not just looking at the graphics, but reasoning, using them to reason about the data. Okay? So, to begin with, categorical data you're very familiar with will be often in the form of tables. And so I thought I'd just quickly go over how you might construct tables. You did a little bit about this in the assignment on the reorganization of tabular data. But let's just have a look at how this is done in R. And there are many, many ways to create tables, and there are different sorts of table data structures, some richer than these base ones that I'm going to show you today. So some fictitious data. We imagine that we're looking for housing as a University of Waterloo student. And so I've got two cities, Kitchener and Waterloo. I've got three varieties of housing: house, apartment, residence. And let's just get some fake data. So these are going to be generated from a Poisson with parameter lambda parameters 50, and get six values to correspond to the 2 times 3 counts that I need. So we'll call this vacancy. And so principally a table is, as you know, a rectangular array. And so we could use a matrix. Here's the matrix. It's going to take the counts. Number of rows will be the length of the city. Number of columns, the length of the housing. I always like to fill in whether I'm going by row or not, so at least I know. I'm very conscious of how the data are filling that matrix. And then the dimension names, the dim names. And this will be list. The name will be city and housing. And and then values of those dimensions will be the values of those two vectors, city and housing. Then I just create as table, and that'll turn it into a table class. And when we print that out, it'll look just as if it were real data there. So you can see a 2 by 3 table of city cross housing. Okay, so that's a very simple way to create that. That's a two-way table, and those are the kind of tables you looked at in, rearranging in the assignment. That could be a multi-way table. So any number of ways, we just have to, instead of a matrix, we're going to use an array. And here my fake data is going to be, just so I can track where things get filled, it'll just be 10, 20, 30, 40, 50, etc. Okay, so the counts are just going to come in that order from 10 to 180 by jumps of 10. As before, the array is going to take the data, the counts, the dimensions, so the length of the city, length of housing, length of term. So I've got city 2 by 3 by 3 terms, fall, winter, spring. And the dimension names, these are going to be the names of how I refer to each dimension by city, housing, and term, and also the values that those three different variates take. So looking at this, I now have a 3-way table, and you'll notice how it's being filled with the first index moving fastest, then second and second fast, etc. So it'll go 10, 20, 30, 40, 50, 60, 70, 80, 90. So you see how the thing is being filled, right? So it's taking these counts and filling that array by changing the first index fastest, then the second fastest, etc. So the first index is going to be the city, second be housing, and third is the term, fall, winter, and spring. Okay, so that's a 3-way table. In this case, a 2 by 3 by 3 array. All right. So that's filling it up, and mainly you have to be cognizant of the order in which it's filling. You can rearrange the dimensions once you've filled it with just an A perm. Here I'm just reversing them. The dimension will be 3, 2, 1. So now the first dimension that's varying quickest is fall, winter, spring, the term, then housing, and then city. So that turns it into a view that looks like two 3 by 3 tables. Okay? So you can rearrange these things, and I think you used that one a little bit in the assignment. If you've got existing data, like South African heart data, we can create a table directly from that data frame. And that's what the table function does. And you just specify the variates that you're looking at creating it. It could be a longer list here of where to take the data from, and DNN, the dimension name names. Okay, that's what the double N is, dimension name names. So we're going to pick off the coronary heart disease and the family history, and that'll construct this 2x2 table of CHD versus FAM-HIST. Getting the counts directly from gathering them up in this data frame. Alternatively, sometimes talk about cross-tabulation. So cross-tabs, X-tabs on this data set, SA heart, and now there's a formula, tilde CHD plus FAM-HIST will produce the same kind of table. Okay, so those are ways to construct tables. One just from the data itself, one from some data that you already have existing, and there are at least two ways of doing that, table and cross-tabs, or X-tabs. Any questions? So, that's why I talk about this kind of data as being crossed, so that every triple in this case of variate values is possible and has some count associated with it. That count may of course be 0, but it's going to appear in the data set here. So this three-way cross table, and here's one that's sitting in our hair eye color, and so the first index is hair. Right, so these are the students we looked at before, the students that have their hair color and their eye color, and then what sex they are. So hair color varying fastest, then eye color. So first, second, and the third one is the sex. And you can get the names, this is the names of the dim names, to find out what the variates are. So you might be starting with that kind of table. We're going to look at subtables of that or alternative tables. So first thing you might do is take a slice of this table. So you think that this is a rectangular array, a three-dimensional array, and we're just going to take different slices. So here I'm looking at the first index, which is hair color, and I'm selecting those people that have black hair, and I'm not selecting anything else. And that's taking that three-dimensional array and taking one slice through that array. The slice that corresponds to those people having black hair. You can think of that as a geometric thing of slicing that, or think of that as that's just conditioning. This is the conditional distribution, the conditional count anyway of eye color versus sex, given that the people have black hair. Okay, so that's a way of thinking about that as a conditioning. Similarly, those with green eye color, taking off that slice, so I'll have the slice that's got hair by sex. And if I take two of these at once, I'm looking at the intersection of these things, so I'm conditioning on those people that have black hair and blue eyes. And all that's left is the last variable is what sex are they, and of these there are only 20 such people in this table, and 11 of which are male. Okay? And of course I can pick off any particular element, which is the intersection of all three of those conditioning values. So there are 3 people that are male, have green eyes, and black hair in this data set. Okay? Any questions on that? So think of that as an array that you're slicing. It's easy in 3D, but it could be in multi-dimensional, more than 3-dimensional rectangular, hyper-rectangular array. And you're looking at slices through it, particularly subsets of it, slices through that array, or conditioning on the variate values. So the geometry and the statistical notions go hand in hand. Collapsing dimensions. So I may want to just collapse the dimensions. So I've got something here called margin table. I do that, apply that to the whole table, and that gives me the entire count. That's the 0-dimensional summary. It's the total in that whole table. So I've collapsed the whole table down to a single number. I could instead collapse it to just one of the margins. So in this case, margin 1, which was the hair color, that's the thing I'm going to preserve. These are going to collapsing all of the table to just that one margin. So no differences in eye color or sex or apparent here. Those are all in those sums. So you see, you take a table and you get the margin of the table, and it's not surprising that that corresponds to a marginal distribution. In fact, that's kind of where the name comes from, right? You always wondered why we call it a marginal distribution. It's just like taking the margins of a table. And so you think about this collapsing is the same as marginalizing in the statistical sense of integrating everything else out, or in discrete case, summing everything else out. So preserving 1 and 2, I've collapsed over the sex. So here, in fact, is the data set ignoring sex. Okay. Any questions? So you get the connection between the statistical ideas, slicing and conditioning, and marginalizing, and this collapsing, this projecting all of the data down onto one dimension. So marginalizing is kind of like a projection, although it's a sum, collapsing the table. When we're doing the table analysis, we sometimes wanted sums. There's a add margins that you can apply to the table or subsets of the table. And so when I add the margins here to this three-way array, what do I have? Well, I still have a three-way array. I've got the hair color, the eye color, and the sex, the 3 different dimensions. But I've got an extra variate, as it were, on each of these, in that I've got, on eye color, I've got a value sum, which is going to be the sum across all of those eye colors. And similarly, for hair color, I've got a sum. And if I'm looking at over the third variate, the sex, I've got male, female, and a value sum. And this sum has got the sums of everything above the tables, right? So I've summed over the sex. Right, so 68 is 36 plus 32. And this 592 is the sum in the whole data set. So you can easily add a margin to the table that corresponds to the sum. You could choose to sum along any particular margin. So summing along the second margin here. The first margin is hair, second is eye, third is sex. So we're summing along the dimension 2, that's summing over these. We're only seeing a sum appear in that one variate, the hair color. Okay? So you can choose the margin that you want to sum over. Okay, so those are some mechanics. Again, summing over 2 margins, just select the 2 margins that you want to sum over. So I'm summing over the first 2, which is hair and eye color, which is where you see these sums appear in both of these tables, but you don't see that third table of summing over the sex. Okay. Proportions. And of course depends on which margin is fixed. So if I take the proportion of the table, this is prop table, and I'm just looking at the 3 significant digits, it's going to turn this proportion into, turn every value into proportions. Right? And so you might imagine, well, how is that going to sum up? What am I summing up here? Well, I think I've not specified any margin, so the fixed margin that these things are going to sum up to, these have to sum up to 1, right? And so now that looks kind of like a probability distribution, these proportions. And so you might think about what model might generate this data, a data of counts. The obvious model here is a multinomial. Okay, so if you think about the counts in our table being Nijk, it's a 3-way table, so 3 subscripts. The total is 592, summing over all of the indices. The multinomial says I've got a probability associated with every one of these cells, right? I've got n, the total 592, and Nijk is just the number in the IJK cell. So I could represent a generative distribution for a table like this. Say these were in fact the probabilities associated with it. These probabilities sum to 1, and I could talk about generating data from this distribution. Okay? Does that make sense? Everybody get that? All right, so you've got a natural kind of multinomial structure for generating counts in a table, provided the total is fixed. If the total wasn't fixed, we might think about, for example, a Poisson model to generate all of the counts. Same thing that I used in the first table that I generated with the city versus housing. Right, I just use a Poisson. But with the total fixed, this looks very much like a multinomial. So to here, let's fix the third margin here. So the sex is fixed. The third margin is the sex. That means the total is fixed for the each of these two tables. Supposing each one of these tables sums to 1, that table sums to 1. Right, I've got a slightly different model. Go back again. See, these numbers are all smaller here, larger here, because the sum of all of these numbers is 2. Right, so think about the sum of these being 1, the sum of these being 1. What would be a possible generative model for this, if the data were generated like this, with fixed numbers of males, fixed numbers of females? Any suggestions? Okay, what would be a reasonable model for just one of these tables? If the total is fixed for that table. Give me an answer. Hypergeometric? Nope. Multinomial. Who said multinomial? Ah, there we go. So a multinomial, this one's going to be a multinomial. That's going to be a multinomial. You liked that beforehand, right? That is a multinomial for this table. It just had 2 separate slices, and all of that summed to 1. Think about a multinomial for each of these. So the model here is kind of a product multinomial. A multinomial for each table. Okay. And the sum over all of the indices but the last one, right, is 1 for each k. Does that make sense? So you can think about it, it's a product multinomial. So the probability of the data in there is whatever you got out of this one, there's a probability of whatever you have for that one. Make sense? Does that make sense? Some of it? Okay, what doesn't? Well, because I've got 2 independent sets of counts. Right? So I have all of these counts. I'm thinking about what's the probability of N1, N2, N11 down to N442. Right? Well, I know the probability of the first bunch of them is here times the probability of the second bunch, that these 2 are independent counts. So it's assuming an independence between those 2 tables. I fixed how many males I'm going to look at. I fixed how many females I'm going to look at. And I'm just looking at the distribution. And that the count in here, the probability in here, does not depend upon how many females what the probability is for females. Okay? Does it make sense now? Good. All right. I could marginalize over 1 N2. And now what's this look like? Well, this looks like, in fact, each column sums to 1. Okay? So I fixed that there's a fixed sum in each one. What would be a probability model for this? Go ahead. So it'll be a multinomial for each column. Right. So that's again going to be a product multinomial. So we've got another product multinomial. There are 4 of them this time. And you just think about what is fixed. So now you've got a table. If I fix certain margins, it suggests a probability model associated with that. And we might be interested in tests about those various proportions. Okay? Does that make sense? All right. Oh yeah, so on the website there's another little R package that we produced here called Tidy Table, which you remember the all of the work we did based on Ehrenberg's rules for tables, etc. So Tidy Table tries to encapsulate that. So if we were to ask for the value of hair eye color, we get this to print out in R. That's the arrangement. And if you look at that, you say, how might I rearrange that? It's a 3-way table. We've talked about how to rearrange 2-way tables. Tidy table, just calling tidy table on this table, and it gives back a rich data structure, but one of its components is a table. And here's the arrangement. The tidy table likes to print this out. It's the same data, just rearranged so that the first index is sex, second is hair color, and the third one is eye color. So you can see that the rules are trying to be applied here in an algorithmic fashion of arranging these tables so that we've got, least variation in columns appearing. We've tried to order things, order the variate values since there's no order between hair color, and we've tried to order these slices as well. So it's a little bigger than what we talked about in 2-way tables. But it does give you some sense that you can look at the numbers. The numbers are comparable here. So we're looking at female, male, or the easiest comparison for each hair color, for each eye color. So for brown eyes, as you might expect, males and females look kind of alike in terms of their hair color. For blue eyes, brown hair seem to be more males than females. For blonde hair, more females than males, but the rest are about the same. So that looks a bit odd. The others look like they're about the same proportions. So just that arrangement should draw your attention to the fact that these numbers here, this table, looks a bit odd. In particular, if you've got blue eyes and female, you seem to be more likely to be blonde than brown hair. Okay? So you can speculate as to why that might be, right? Whether this is the dyed color of the person's hair or what. The truth of this matter is it's just completely fictitious. Somebody split this on sex. They made these things up just to look like this, and for you to actually spot that. But the tidy table allows that to sort of pop up at you fairly quickly. So the data here is all true except for the variate sex. That's completely fake. Okay? And it just probably reveals the person's prejudice when they set this up, that they thought women would be dyeing their hair blonde more often if they had blue eyes than men would be dyeing their hair blonde if they had blue eyes. Or if you look at proportions, again, you could do the proportions here and compare this table with the tidy table version. And the tidy table actually tries to get rid of these decimal places and give you the number of units. So tidy table is there for you. It's not on CRAN. I probably should put it on CRAN. but it's there for you to use on the course website. And you can imagine how you might develop algorithms to try and implement those rules that we do eyeballing, especially for multi-weight tables. Any questions? All right, let's switch to something much more obviously visual. Back to this eikosogram. And eikosogram is really, I want you to think about this as, this is the picture of what probability is. And this embeds probability. And probability in its essence can be understood entirely with just categorical data. And here we often would just be using binary data, just have two different categories. But it has a particular structure. So once you think that we've got a unit square, and we imagine that this is the frame. This frames our probability statement. So any symbolic thing, it's going to be conditional on the frame that we're looking at. And suppose y has two values, y1 and y2, and it takes value y1 with probability 1/3. So this vertical axis is always the conditional probability of this category. Okay, so we've got probability y1. Y equals y1 given this frame is 1/3. Probability y equals y2 given this frame is 1 minus 1/3 or 2/3. Okay. So the conditional probability is that height, but since this is only one variable, right? It's also the marginal probability, and this area here is the probability. So that's also 1 times 1/3. So that area is the probability as well. Just happens to be we're multiplying a width of 1. Okay? Any questions? So that's the simplest one that you can imagine. Let's imagine 3 values. So think about tossing 2 coins, tossing them simultaneously, 2 coins at once, and we have 3 events. They both land tails, they both land heads, or one is heads and one is tail, and I'm not distinguishing between which is which. So you know yourself that the probability of both landing heads is going to be 1/4. Probability of one landing heads and one landing tails, well, that's going to be 1/2, 3/4 minus 1/4. And the probability of both landing tails is going to be 1/4, 1 minus 3/4. Okay. And so this corresponds, this picture, the areas being the probabilities, corresponds exactly to this symbolic representation we have. All right? So far, so good? So now imagine that I toss the coins, first one, then the other. Okay? So this is an outcome tree. So you imagine that I'm proceeding in time from left to right. So this is the first coin toss. It either is a head or it's a tail. Then I toss the second coin. So this is either a head or a tail. Or it's a head or a tail. So that's two coin tosses. If I think about, I get one head, one tail, that corresponds to a subset here. I can get a head on the first coin and a tail on the second, or a tail on the first coin and a head on the second. So the event of one head, one tail is that subtree. Okay? So we could have, this could be a much more complex thing with multiple branches at each node and just sort of organizing this. But what makes this interesting is now I've kind of got 2 random variates, but I want to look at 2 binary variates, coin 1 and coin 2. Okay? So this matches an eikosogram very nicely. So if I toss the first coin, let's assume that I get heads. So now I'm just looking at, if I've got heads, the second coin, y, gets heads with probability 1/2 and tails with probability 1/2. So this picture now represents this symbolic statement. Probability of y is heads, given heads, x is heads, and this frame is 1/2, right? Also, the probability y is tails, given x is heads, and this frame is 1 minus 1/2 or 1/2. So this picture matches exactly this symbolic representation. I have 2 of these. I have one for when x is heads, so when the first coin was heads, and when the first coin was tails. They each have their own little frame and their own probability associated with it. I want to put them together. To put them together, I need to know what's the probability of x being heads, what's the probability of x being tails. Those are both going to be a half. So putting together, I can have this eikosogram. Now you see that on this axis, I've got one frame there for the x equals heads, another frame for the x equals tails. I put them together according to the probability. So probability x is a heads is a half, so that's a width of a half, and similarly for tails. But from this picture, I can talk about, since area is probability, I can talk about the probability that y is heads and x is tails. That only happens in this bottom left corner. So the probability of that event is the area there. That area, you know, is just a rectangle. It's going to be width times height. The width is this marginal probability. The height is whatever that conditional probability is. It's a half. So we get probability y being heads and x being heads is a quarter. Right? Probability of y being heads and x being tails is a quarter. Each one of these are all a quarter, those four squares inside. And so if you're thinking about one of them being heads and one of them being tails, that's going to be this probability, y is heads, x is tails, and this probability up here, y is tails and x is heads. Quarter plus a quarter, that's a half. And so that's how you see why you get a half for the problem, for the event that one of them is heads and the other is tails. But you immediately have this representation here, which makes sense. Now symbolically, we spent some time in some course to tell you that this conditional probability was actually this divided by that. But now it's obvious, right? It's just the area of the rectangle. This is the height of the rectangle on the left, and this is the width of the rectangle. And that's the rectangle that you want. Okay? So these things naturally match. Any questions? All right. So the two different representations here, depending on how y is defined, these identify, if you're only interested in these three events, you can get them from both of these eikosograms. However, from this one, you can get the whole joint distribution. So this is the joint distribution of both of these coin tosses. This, you don't have the whole thing. You've just got the probability distribution of these three events. So I can get any of those events from this. I can get the conditional probability of y given x. I can get the marginal probability of x. And if I want the probability of heads, well, that's surely got to be all of this. Y is heads. That's going to be all of this yellow. So the probability of the second coin is heads is this area here plus that area there, which is a quarter plus a quarter is a half. See, this is a rectangle, it's a half times 1. Okay? So let's think of a different example. So one thing you might notice that this is flat, so this is pretty boring. And what this says is the probability y is heads given x is heads is the same as y is heads given x is tails, is the same as y is heads. Half, 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 everywhere. We have a way of describing that. We say that y and x are independent. So when you see that flat line there, that seems like it's something about independence. Okay, let's go on. So here they're not. So here I've got the probability that y is 1 given x is 1 is 1/3. Probability y is 1 given x is 2 is a half. So not the same. But the probability is still area. The probability y is 1 and x is 1 is that area, so that's going to be 1/3 the height times the width is a quarter. So that's going to be 1/12. Okay? Make sense? So the areas of these little rectangles are all going to be those joint probabilities. The width of any of these vertical bars is going to be that marginal probability of x, and the height of these lines inside is the conditional probability of y given x. Okay? And these guys are not independent because the probability y taking value 1 depends on whether x was 1 or whether x is 2. There is no horizontal line here. Okay? They're on different levels. I could switch this around. If I have this distribution here, where I've got mainly written in terms of the conditional distribution of y given x, I may want to turn that around and write that in terms of x given y. This should be the same distribution. So this little square in the bottom left here has y equals 1 and x equals 1. And this little square has x equals 1 and y equals 1, so these better be the same area. And if you check, that's going to be 1/3 times 1/4 and 2/11. So what was that? 1/3 times 1/4 was 1/12, right? And we got 2/11 is that height there, times the width, 11/24 is 2/24 or 1/12. So those are the same areas. They've got to match if it's the same thing to preserve. So when you take this, you can construct this from that just by figuring out what areas match. And so if we look at that bottom left area and write it out symbolically, it's going to be the height, which is that conditional probability, times this marginal probability, the width. This one's going to be that height, which is that conditional probability, times that marginal probability. They're the same area. And that, ladies and gentlemen, is all there is to Bayes' theorem. All this Bayesian stuff, Bayes' theorem looks really advanced. It's not. It's trivial. Never be afraid of Bayes' theorem. If you can figure out the areas of rectangles, you can see why this theorem holds. The eikosogram kind of embeds the Bayes' theorem in it. That's why I say it's the picture of probability. Because the rules of probability and calculated things are all about equating rectangular areas. Okay? So all you have to know is, if I'm going to calculate what is this, I need to know the width. That means I need to know the probability that y equals 1. Well, y equals 1 is, over here, it's that height times that height, plus that height times that width. Sorry, that height times that width plus that height times that width. Right? That's the probability y equals 1. That better be the width of this whole thing because it has height 1. It's that simple. And if you look at that and write that out symbolically, those are all the rules of probability that seemed esoteric maybe when you first encountered them, but they're trivial. Okay? So that's Bayes' theorem. Any questions? Okay, let's do something fun. Let's do the Monty Hall problem. Monty Hall died this year. I don't know if anybody of you guys would know him. It was a TV show, I don't know when, in the 1960s, 1970s, 1980s, a long time. And it went something like this. Let's make a deal. Monty Hall's Canadian, by the way. Let's make a deal. You've got 3 doors. You're the contestant. You choose one of door A, B, or C. You win whatever's behind the door that you choose. You get to take that home. Behind one of these doors is a brand new car, your favorite car. Okay? Behind the other 2 doors is something you don't want, a goat. Okay? So if you choose a goat, you have to take the goat home. So what you want to do is choose the door that has the car behind it. Everybody understand this? Simple enough. So you make your choice. And Monty says, okay, great, you chose that door, that's fantastic. Let me show you what's behind one of the other doors. And he opens one of the doors that you didn't show. So if you chose A, he'll show you what's behind one of B or C. And that's not going to be a car. That's going to be a goat. So now you know that you got 2 doors and one of them has the car. And he says, do you want to switch? Do you want to change your mind? Do you want to switch doors? Or don't you? Maybe it doesn't matter. There's 2 doors. It's behind one of them, probability 1 and 2. Right? So the question is, does it matter whether you should switch or keep the door? Everybody with me? So that's the game. And you do this all the time. It's a kind of, I mean, you probably will find some of these on YouTube. See if you can find some old things with people jumping up and down and trying to decide whether to switch. So if you switch, you get, so he's going to, so if you select door C, he opens doors B and says, do you want to switch? And so the reasoning often goes that it doesn't matter, just pick, you know, switch or don't switch, doesn't matter. Okay. So here we go. So either A or C seems like a reasonable choice. Let's think about this. You want to frame this problem with as an outcome diagram. And there are three levels going on here. The first one that you have to think about is that Monty has to place the car somewhere. So you got three doors, A, B, and C. Monty's going to place the car behind door A or B or C. Then, given that it's placed, you come there as a contestant, and you're going to choose one of A, B, or C. If he puts it behind A, you're going to choose A, B, or C. Puts it behind B, you still have the three choices. Every time you've got those three choices. So you choose a door. Okay, and then he reveals something. So if the car is behind door A and you've chosen door A, he can reveal B or C. If the car is behind door A and you've chosen B, he can only choose C. If the car is behind door A and you've chosen C, he can only reveal B. Okay, because he's not going to reveal the car. He's only going to reveal the goat. So if you've chosen the car, he's got a choice. If you've chosen the goat, well, he's got to pick the other goat. Okay? So you think about what might have happened. Well, let's suppose you chose door C and Monty revealed door B. Then the only place that happens, you choose C and he reveals B. Can't happen there. Can only happen in these two instances. So that's the subtree that corresponds to the data that you have. Okay? So we're going to break this down with drawings now. Everybody get the framework? All right? Okay. So that's the event that we've observed is what's shown in solid there. You chose C, and he reveals B, which means he didn't put the car behind B. So what we want to do is determine this probability. What's the probability? We've picked C, remember. What's the probability that the car is behind door C, given I selected door C and door B was revealed to have a goat behind it? So that's the conditioning event. Okay? So let's look at this. Let's suppose that we're just going to look at the case. You've already chosen door C. It doesn't matter which one you chose. They're all the same. I've chosen door C, and that's the only case we're looking at. So Monty has two choices. He can open door A or he can open door B. So here's our frame. The true location of the car is A, B, or C. You've chosen C, and Monty's about to open the door. Okay? So what I want to know is what's the probability of opening door B or opening door A, given the true location is at any one of these marginal ones. Okay? So let's just go through this. Suppose I look at this first one. A conditioning is that the true location is A, right? And you've chosen C. What's the probability that Monty will reveal door B? Yeah? 100%. Probability is 1. He's not going to reveal door A because that shows the car. So you can color that in. Okay? Now if the doors if the car is behind door B, what's the probability that Monty reveals door B? Nada, right? He's not going to show that. That would be dumb. So that's 0. If the car is behind door C, which is the door you chose, Monty can reveal door B or door A. Right? What's the probability he's going to reveal door B? Anyone? 0.5? How do you know? Is it? We don't know. Monty may be a weird guy that really likes B. We don't know whether that's a half or not. Okay? Monty's got some predilection for door B, right? So let's call that P. So he's going to reveal door B with some probability P, which is Monty's personal probability that he likes to reveal door B. Maybe that's a coin toss, maybe it's something else. But it's P. Okay? So does that seem to capture what's going on here? Those are all of the probabilities, all of the possible events. Here's the probability we want. What's the probability that it's at the car is behind door C, given we chose C, and Monty reveals B? That's the probability we want. Here's the picture of what's going on. So the conditioning event is that Monty has revealed B here. So we've already got, this whole thing is we've chosen C. Where has Monty revealed B? Well, he's revealed it wherever it's yellow. Okay? So the only part of this diagram that matters in answering the problem is the yellow bit. Of that yellow bit, what proportion of that yellow bit has the car behind door C? Well, it's this area divided by the sum of the two, right? So in this case, it's P times a third divided by P times a third plus 1 times a third. So that conditional probability is P over P plus 1. Okay? So if Monty hates door B, right? He's not going to reveal what's behind door B. If that P is 0, right, it's best to switch. Because the probability of it being behind door C is 0. So better to switch. Okay? If P is 1, if he really always wants to reveal behind door B, then this is going to be 1 divided by 1 plus 1. It's going to be a half. Doesn't matter. You can switch or not switch. And anything in between, it's a higher probability that the car is behind door A. It's better to switch. So overall, it's better to switch. Okay? Very, very simple analysis. If you look at solutions on the internet, most of them will pick P equals a half, but that doesn't matter. So in one case, I mean, again, nobody models Monty. You have to figure out what's Monty doing. Does that make sense? So that's probably a good place to stop. So the Monty Hall problem, there's no mystery there at all. You just have to lay that out properly with the outcome diagram. What is the event that we're looking at? What conditional probability do we want? Draw the eikosogram and reason with that eikosogram. Okay? It really simplifies things, that visual reasoning. All right, till next time.